Hi class, we continue our study in chapter 4 talking about this concept of exponential functions, which we defined in section 4.1 by moving into section 4.3. This is all about graphing what exponential functions are going to look like. Okay, so let's talk about doing a problem by hand. Suppose I give you this. I say graph f of x is equal to 2 to the x power by hand. So the way you would graph this by hand is you would need to find some test points, right? So first, let's do some input-output pairs. And so what I'm going to do for x is I'm going to pick the values -3, -2, -1, 0, 1, 2, and 3. Okay, this lets me know what the graph looks like at the negative side, at 0, and then at the positive side. All right, so when I plug this in, right, like this is 2 to the x power. 2 to the -3, well, I know that comes down, right, to make it positive. So when x is equal to -3, the value of function is 1/8. See the same thing with the squared term, right? Comes down, makes it positive, it's 1/4. -1 comes down, makes it positive, is just 1/2. You plug 0 in, right? Anything to the 0 power is just equal to 1. Then 2 to the first power is just 2. 2 to the squared is equal to 4. 2 cubed is equal to 8. So note that as the x value increases by 1, the value of y is just multiplied by 2, the base. So it looks like we have some fractions, 1, and then some positive numbers. So when I go to graph this, it's going to look like this. So here's -3 1/8, -1 1/2, 1/4, or -2 1/4, -1 1/2, 0 1, 1 2, 2 4, 3 8. Notice how it has this whoosh, shoots right up like this. This is a key feature of the exponential function. And this is important. The value of the function can never go negative. Okay, so it's going to butt up, right, against this x-axis here. It's actually going to be what's called a horizontal asymptote. So you can verify this by plotting this in your graphing calculator, and you'll see that your graphing calculator produces this same exact graph, just like this. Okay, so the graph of an exponential function is called this exponential curve. And for an exponential function of the form y is equal to a times b to the x. Okay, so b is the base, x is the exponent, and a is just going to be some number, some constant. If the value of x increases by 1, the value of y is multiplied by b. Okay, so in other words, if the input increases by 1, the output is multiplied by b. So if the base is 5, when you increase x by 1, you multiply that by 5. All right, so let's let f of x equal a to the bx if the a number is greater than 0. Okay, this is for a greater than 0. If b is greater than 1, so the base is greater 1, then the exponential function is what we call increasing, and we say the function grows exponentially. So whenever a is greater than 0 and b is greater than 1, the graph is going to look like this. Okay, something like this. Now, if b is some number between 0 and 1, like 1/2, the function is decreasing, and we say the function decays exponentially. So the graph will look like this. It's kind of like the flip of this. It'll be high for negative values and then whoop, get low this way, like so. All right, so for the graph of an exponential function of the form y is equal to a times b to the x, the y-intercept, remember when x is equal to 0, b to the 0 just goes to 1, so 1 times a. The y-intercept is always 0, comma a, always, always. Okay, here's a warning. For the graph of the exponential form y is equal to b to the x, rather than y is equal to ab to the x, the y-intercept, this is important, is not 0b. Okay, it's not. By writing y is equal to b to the x as 1 times b to the x, we see that the y-intercept is actually 0, comma 1. So if there's nothing in front of the b, the y-intercept is always going to be 0, comma 1. Always, always. All right, let's look at this one. Let's investigate it. Let's let f of x is equal to 6 times 1/2 to the x power. Let's find the y-intercept. Let's find the x-intercept, if there is one. And let's graph this by hand. Okay, so we see that 6 in front is the value of the a. So the y-intercept is 0, comma a, or 0, comma 6. So the y-intercept occurs at 0, comma 6 here. All right, by the base multiplier property, as the value of x increases by 1, the value of y is multiplied by 1/2. So values are shown in this table below. So as you increase by 1, you multiply by 1/2. So like 6 times 1/2 is 3. Increase by 1. 3 times, 3 times 1/2 is 3/2. Then increase x by 1. 3/2 times 1/2 is 3/4, and so on. So what you're seeing here, when we have a value, it becomes smaller, but no number of halving will give a result that is equal to 0. So as x grows large, y will become extremely close, but never equal to 0. Likewise, the graph of f gets arbitrarily close, but never reaches the x-axis. In this case, we call the x-axis a horizontal asymptote. So we conclude that the function f has no x-intercept. So when you go back, I'm sorry to go back, but you're looking at both these graphs, notice how they never touch the x-axis, right? That means there's no x-intercept, never, never. Okay, so let's now graph this by hand. So when you graph this by hand, you're going to plot some points that we just found, and you're going to see that the graph gets exponentially smaller like this. So it starts at 0, 6, then we saw that 1, 3, 2, 3/2, 3, 3/4, and so on. Now, just as a sidebar, your homework in math lab this week will ask you to pick plots to show what it looks like. So it'll give you the graph and say, hey, what does this function look like? And you'll have to pick. On your journal assignment next week, you'll have to plot one by hand, but it'll be very, very simple. And these fractional values will never need to be perfect, just so you get a good idea of what the graph looks like. All right, so now let's talk about the following. If f of x is equal to negative a times b to the x and g of x is equal to a to the b to the x, these are reflections of each other in the x-axis. So what the negative value on the a does is it flips the graph. So the graph of the exponential function f of x is equal to a to the b to the x does not have an x-intercept, never, and the x-intercept is, the x-axis is always the horizontal axis. So if a is greater than 0, all right, and this is b is greater than 1, the graph is going to look like this. If they have this negative number in front of a, all it does is flip it, and it goes downward like this, okay? If b is between 0 and 1 and a is positive, the graph looks like this, all right? But if a is negative, then the graph just flips, and it looks like this. Okay, so one more thing, the domain of the exponential function is a set of all real numbers, and the range of the exponential function is a set of all positive real numbers. So an exponential function, as long as a is greater than 0, all right, will never be any negative numbers. And if the a is less than 0, then the range is a set of all negative numbers. Okay, it's whatever the range is, it's either all positive if a is greater than 0, or all negative if a is less than 0. All right, so the graph of the exponential function f is shown below. All right, so I see something like this. All right, so let's find f of 2. Let's find f of x when x is equal to 2. Let's find x, if possible, when f of x is equal to 0. All right, so I have the graph up here. So we see here the blue arrow shows that when the input is 2, okay, this leads to x, or the value of the function being 8. All right, so f of 2 is equal to 8. So the red arrow here, all right, shows that when the output y is equal to 2, that the input was x is equal to negative 2. So we have x is equal to negative 2 when the function is equal to 2. And recall that the graph of the exponential functions gets close to but never reaches the x-axis. So there is no value of x where f of x is going to be equal to 0. All right, thanks, class.